All right, so in this video, we will talk about the one sample confidence interval for proportions. And I'm going to work out an example in detail so you know exactly what needs to be done and how you check the conditions and how do you go through the four major steps. So let's say you're interested to know the percentage of students that like the food at your school. And we don't know the number of students at your school. You may have 1,000, you may have 10,000. I don't know what that number is, and I could care less. But let's say you took 100 students, you took a sample of 100, and you asked each one of them whether or not they like the food. And you discover that 60 of them do like the food, which means 40 of them do not. And you want to be able to draw a conclusion about the entire student population on whether or not they like the food. Again, you're talking about percentages, ratios. And the only condition you have for yourself is you want to be 90% confidence. It's a fairly good confidence level. It's not superb like you want to be 99% confidence, but it's not pathetic like you want to be 20% confidence. So 90% is reasonable, is a reasonable request. Okay, so how do you draw a conclusion about the entire population of students at your school based on this 100? So we're going to go through the 4 steps we are accustomed to. The first step has two pieces to it. One is just to figure out what you're trying to find. If you don't know what you're looking for, you may as well not do the problem. Okay, so what we are interested in is to estimate the true proportion. We're talking about the parameter P of students that like the cafeteria food. Okay, again, it is a proportion. It is a ratio. It is a percentage. Okay, we're not talking about means here. That's what you want to know with this type of confidence level. And it's important to locate yourself, as I have mentioned in many videos. So this is going to help us, first of all, just locate yourself, because it's important to know where you are. But it's also helpful when you want to do the calculation in step 3. So clearly this is a one sample. We don't have 2 schools and 2 samples and 2 populations. We have one sample. This is a Z, not a T. By the way, whenever you deal with proportions, you never use the T distribution at all. So we're talking about a Z. And we're interested in a confidence interval. We're not interested in conducting a hypothesis test. And this is for proportions. It's not for means. Okay, so there are 4 pieces to it. 1 versus 2, Z versus T, interval versus test, hypothesis testing, and then proportion versus means. So you've got to be able to list those 4 pieces. Okay. Before I proceed to step 2, I just wrote these numbers in green because they come in handy. So these are the number of students that like the food. This is the sample size, and therefore your statistic, right? This is the proportion of the sample. That's why it's a p hat, not p. Nobody knows p. That's what we are trying to estimate. Is always x over n, which is 60%, and therefore q is 0.4. 0.6 plus 0.4 is 1. Or you could do 40 divided by 100, right? Because if x is 60, then those who don't like the food is 40, okay? So you could figure this out in 2 ways. All right? So let's go through the conditions. 3 conditions always are randomness, how was the sample taken? Independence, how were the observations? How are the observations? Are they dependent or not? And then, of course, normality, because without normality, we couldn't do this step 3, okay? So we need the normality. So for randomness, we were told that you chose a sample of 100. We don't know how the sample was taken, right? So we have to proceed with extreme caution, I wrote. Now, if you were the consultant for this school, instead of saying we will proceed with extreme caution and continue, you're going to have to go back and figure out how was that 100 taken. And if it wasn't sampled properly, you would have to do it in such a way that this 100 represents the entire students population. So you'll have freshmen, sophomores, juniors, and seniors. You'll have male and females. You'll have day students versus non-day students. You'll have any variable that you think will impact the answers. So for example, day students, they're home, and so they're used to eating home food, food at home, and therefore they might be pickier with cafeteria food because they're used to a better food at home. So whatever variable might impact people's responses, you've got to bring that into the conversation. So this 100 has to represent the population of interest. Okay, so that's the first one, randomness. Independence, when you're sampling that 100 students, how were they chosen? In other words, let's say one of them's name is Jane, and you asked her, do you like the food or not? And it doesn't matter what she says. Is she back as part of the 100, or she's out and now you're dealing with 99 students only? If it is done with replacement, if Jane is back in the pool, which means she has the ability, or there is a probability she'll be picked again, and she will answer the same way, of course, again, then the events are independent, which means the observations are independent, and that's the thing you want. If you're not sure how it was conducted, or you didn't do it with replacements, then you have to check the 10% condition. Now, since I took a sample of 100, I'm assuming the school has at least 1,000 students. If the answer is no, let's say the school only has 700 kids, then the 10% condition is not fulfilled. Once again, if the observations are taken with replacement, you don't need to check the 10% condition. If not, or if you're not sure, then you need to check the 10% condition. So this only depends on whether this is done properly. Okay, so that's the idea of independence. And then, of course, normality. Now, we didn't here with p hats, statistic, and p, the parameter. Now, we know for a fact that p hat follows a binomial distribution. Okay, like the food, don't like the food, right? There are two outcomes. Sample size is fixed. Events are independent, hopefully, right? And then the probability of success, this is the probability of success, and this is the probability of failure, are fixed. They're not changing. So we know p hat follows a binomial distribution. We know that for a fact. The question is, does it follow a normal distribution? So we need to check what we call the NP and NQ more than 10, which means we need to use the normal approximation to the binomial. We know it is a binomial. P hat is always a binomial. So the only thing you need to make sure of is to jump from the word binomial to normal. And the trick we learned was to check on the normal approximation to the binomial, which means this is the condition that you need to check. We know NP is 60, and we know NQ is 40. Remember, NP is exactly X. If you cross multiply, X is NP. Well, we know X is 60, okay? So 60 is more than 10, and NQ is more than 10. So according to the normal approximation to the binomial, we can safely say that p hat follows a normal distribution, and therefore we're able to perform the calculation. I'm going to show you the calculation in two ways. The first way is by hand, actually on the calculator, and the second one by hand. So recall confidence interval. This is the blueprint. It's always the statistic minus the margin of error, statistic plus margin of error. And the margin of error is either Z or T. We don't know T yet, so it's Z. Whenever you deal with proportions, it's always a Z. And my standard deviation of my statistic has happened to be P1 minus P over N square roots. Remember this, okay? So this translates into this for our problem. And of course, the margin of error is just this piece that you're adding and subtracting. And so what do we need? We need p hats, which we do have. We have n. The only thing we don't know is z. So to calculate this interval, we need z. To find the location called z, you have to do inverse norm of my area. We want to be 90% confidence. So we need to pause here for a second. I'll do it in red. We want to be 90% confidence. So this is my 90% confidence interval. If this is 90% and you're looking for this particular location called Z, feel free to look for that one. It doesn't matter. It's just going to be the negative of what you're going to find here. The area to the left of this location is not 90, but it is also an extra 5%. So make sure that you write 0.95, not 0.90, okay? Notice I didn't write mean and the mean and standard deviation. It's always 0.1 for a standard normal. So again, it's not inverse norm of 0.90, but it is inverse norm of 0.95, okay? So that's my Z value. I calculated the margin of error for you separately, basically this quantity here, or that quantity, which is this. This is really helpful because number one, you could just do 0.6 minus that, and then 0.6 plus that. But also, if you want to control the sample size, we usually play around with the margin of error, so it's important to know how to figure out the margin of error by itself. Okay, so I just plugged in. We know p hat is 0.6. We know 1 minus p hat, which is q hat, is 0.4. We know n is 100. We already calculated z. Here it is. And here is my p hats. And if you compute these two values, you're going to get this. Let me just pause here for a second and say something about p hats. So I'll do it also in red. Notice your confidence interval that you are interested in, whatever you're looking for. So in our case, we found 0.51942 and 0.68 and some change, 0.58. Notice the middle of your confidence interval is always your statistic. In our case, it's p hats. In other words, if you average these two, you're going to get 0.6. So we're not trying to find a confidence interval for the statistic. That's silly. We know the statistic is always in the interval. In fact, it is in the dead center. Why? Because these two values are conjugates. A minus B, A plus B. So if this is A minus B, and this is A plus B, the middle number is called A, which is the seed. And in our case, it's always the statistic, okay? So please, whenever you're looking for confidence interval, you're trying to figure out, you're dealing with the parameter, either P or mu. You're not dealing with X bar and P hats, because those are always in the center of your interval. Okay, so that's the confidence interval. And the way you interpret it, I'll go to step 4 and then I'll go back to the second method. You don't say that I am 90% confident that my proportion is here. That's silly. The proportion is either here or not here. The P you're interested in, this one, it's either here or it's not here. That's not how you say it. The intervals are the variables, and your P is a number, is fixed, it doesn't move. The way you say it is, we are 90% confident that the true proportion of students who like the cafeteria food is captured by the interval. Okay? You don't say we are 90% confident that the true proportion is here. That's silly. The P is either here or not here. It's either a 0% chance or a 100% chance. P is fixed, it's a number. And the intervals are the variables. And we're saying about 90% will capture the true proportion P. We actually still don't know what it is. We don't know what that P is. But we're 90% confident that that number we're looking for is stuck somewhere in here, is captured by this interval. Let's go back to step 3, which is to perform the calculation. This is how you do it by hand. And by hand doesn't mean everything has to be done by hand, right? You could use the calculator to compute some silly numbers like this one. But the actual graphing calculator method, I called it step 3 prime. You're going to go to stats, you're going to go to tests, and you scroll down to A. This is where this is helpful. When you locate yourself, you'll know exactly where to go. You're going to go to A, which is one sample, proportion Z interval. Notice all the four things are captured here. 1 versus 2, proportion not means, Z not T, interval not test. Okay? Click on this. You enter your X, you enter your N, you enter your confidence level. Now, your confidence interval is 90%. When we were looking for Z, we did inverse norm of 0.95. But in here, you write exactly what you're looking for. The confidence level is 90% because that's what we were told, okay? Whatever we were told is exactly what you write in here, okay? And you click on calculate, and you're going to get that for free, okay? So this is probably much faster, but it's important to know how to do it by hand because you know exactly what goes into your interval. See, in here, you don't see necessarily that p hat is in the center of this interval unless you do it by hand. So you could see it. X minus y, x plus y. So x is in the middle of my interval. Make sense? All right, that should end this video.